Greetings and welcome to part 4 of the calculus series, and in this video we'll be looking at the quotient rule. The success criteria for this lesson would be for students to be able to apply the quotient rule for differentiation. In part 1 of the calculus series, we started on the concept of the derivative. For any given function at any given point, the derivative will tell us the gradient of the tangent at that point. We can also call it the gradient function. We have learned that for power functions, the derivative of ax to the power of n would be anx to the power of n minus 1. So basically, power to the front and the power minus 1. Now, aside from the power rule that only applies to power functions, we have also come across a few general rules over the past few videos. In part 1, we covered the sum and difference rules that states that you can add or subtract the functions together before or after finding the derivatives. In part 2, we learned about the chain rule, and that applies to the composition of any functions. You can also interpret it as substituting some part of the function as, say, a function u, and differentiating that function with respect to u before multiplying the chain, which is du dx, differentiating u with respect to x. In part 3, we studied the product rule, and that applies to the derivatives of a product of two or more functions. In part 4 today, we will start on the quotient rule. But before we go into the quotient rule, let's begin with a problem. So recalling the product rule that you've learned in the last video, differentiate x squared plus 1 over 5x minus 3. Pause the video here and give this question a good try. Okay, so here we have the product rule, but we don't quite have a product. So we need to turn this into a product. So we'll just shift the 5x minus 3 to the numerator by changing it to 5x minus 3 to the power of negative 1. So here we can set the function u to be x squared plus 1 and the function v to be 5x minus 3 to the power of negative 1. We can compute our du dx, that will give us 2x. Now to compute dv dx, again we'll still need to apply the chain rule. So first we can substitute 5x minus 3 to be our g. So we'll differentiate g to the power of negative 1 with respect to g first, and that will give us negative g to the power of negative 2. However, we still must multiply by the chain, the dg dx. And dg dx is just differentiating 5x minus 3 with respect to x, and that will give us 5. So substituting away the g and replacing the dg dx with 5, this is what we get for dv dx. Now, by the product rule, we are going to get the u dv dx plus the v du dx, and we just have to simplify all this. Of course, we can first change them to positive index notation. This is what we'll get. So two algebraic fractions. But notice that in the second algebraic fraction, I have 5x minus 3 in the denominator. I can combine them to the same algebraic fraction by multiplying 5x minus 3 to the top and bottom of that algebraic fraction. So now they have the same denominator. We can add them together. So the numerator will be 5x squared minus 6x minus 5, and the denominator will be 5x minus 3 whole thing squared. And that's our final answer. Wait a minute, did we just differentiate an algebraic fraction, which is also a quotient, without even learning what the quotient rule is? So maybe we don't need the quotient rule after all, and we can end this video early and skip to part 5. Well, Professor Calculus seems to disagree, and he thinks that we should teach it anyway. He is sort of right that the quotient rule is faster, but that would also mean memorizing one more formula. Fine, let's derive and apply the quotient rule. Well, actually, from what we've just seen, it turns out that the quotient rule is the product rule in disguise. So we're going to prove it from the product rule. So the product rule states that when you differentiate u times v, you get u dv dx plus v du dx. Now we're going to try to change this into the quotient rule. So the quotient rule, we want to differentiate u over v. So how can I change it? I'll convert all the v's to v to the power of -1. So I add a -1 here, a -1 here, and a -1 here. Now, the first part, I need to differentiate v to the power of -1 with respect to x. So I need to apply the chain rule. So I first differentiate v to the power of -1 with respect to v, and I multiply by the chain, the dv dx. For the second term, I'm just going to change v back to the denominator, so I'll get 1 over v times du dx. Now let's go back to the first term. I need to differentiate v to the power of -1 with respect to v, so that's going to give me negative v to the power of -2. Now we can simplify that, change it to positive index notation, we'll get negative u over v squared. For the second term, I'm going to change the 1 over v to v over v squared by multiplying a v to the numerator and denominator so that I have common denominators on both terms. This way I can combine both fractions together, and this gives me the quotient rule. So now that we know the quotient rule, let's go back to problem 1 and solve it again, but this time using the quotient rule. So pause the video here and give this question a good try. Alright, first we need to set up our quotient rule. We need to define the numerator to be our function u and our denominator to be our function v. We can differentiate u with respect to x, that will give us 2x. Differentiating v with respect to x will give us 5. Now we need to apply the quotient rule. Firstly, we'll do the denominator, v squared. That part is the easiest. It will just be 5x minus 3 squared. But for the numerator, please be careful here. V du dx comes before u dv dx. If you swap these two terms around, you're going to get the negative of the correct answer. So v du dx gives us 5x minus 3 times 2x, and we will subtract away the u dv dx, which is x squared plus 1 times 5. So we can simplify the numerator. That will give us 5x squared minus 6x minus 5 over a denominator of 5x minus 3 squared. Notice it is the same solution as when we use the product rule. Two different methods should give you the same answer if they are both valid methods. Moving on to problem 2. Differentiate these two following expressions. Pause the video here and give this question a good try. Once again, we'll set u to be the numerator, 3x, and v to be the denominator, square root of 4x minus 1. Du dx will just be 3. For dv dx, we first have to apply the chain rule, so we'll let g equals to 4x minus 1. Instead of differentiating it by x, we'll differentiate it by g. So dv dg will give us 1 over 2 root g. But we have to multiply by the chain, the dg dx, and dg dx will just give us 4. So if we replace the g with square root of 4x minus 1, this is what we'll get. Now we can apply the quotient rule. So first, we have our v du dx minus our u dv dx and dividing by v squared. Now, look at our numerator. It looks quite complicated, but we can make square root of 4x minus 1 the common denominator for both terms. So I'll multiply a root 4x minus 1 to the numerator and denominator for the first term in the numerator, and I'll get 12x minus 3 over square root of 4x minus 1. This way I can combine the numerator into a single fraction, and the denominator in the numerator, the square root 4x minus 1, I can bring it down to the denominator. So in total, what I'll get is 6x minus 3. So the 6x comes from 12x minus 6x. And the denominator, I'll multiply the roots of 4x minus 1 with 4x minus 1. That gives me 4x minus 1 to the power of 1.5. And that will be our final answer. For part B, it's a little bit more complicated. First, if we want to differentiate this with respect to x, we should apply the chain rule first. So we'll let the algebraic fraction be g. So I'm differentiating g to the power of 3 with respect to x. So what I do is I differentiate it with respect to g first. So I'll differentiate g cubed with respect to g. That gives me 3g squared. And I have to multiply by the chain, the dg dx. And let's just replace g back with the algebraic fraction that we started off with. So this is what we have. So we've done the first part, but we haven't differentiated the algebraic fraction 5x plus 1 over 6x minus 1 with respect to x yet. To do that, we'll need the quotient rule. So let's set up u to be the numerator, 5x plus 1, v to be the denominator, 6x minus 1. This one's much easier. du dx is just 5, dv dx is just 6. So to apply our quotient rule, we'll have our v du dx minus our u dv dx over the v squared. The numerator, the x's will all cancel out nicely, and I'll just get negative 11 over 6x minus 1 squared. So now that I've differentiated the algebraic fraction, I'll just have to multiply them all together and get my final answer of negative 33 times of 5x plus 1 squared over 6x minus 1 to the power of 4. So this in total will be our final answer. So before we end, let's go back and reflect on the success criteria that we've set up at the start of the lesson. Are you now able to apply the quotient rule for differentiation? Now, I've also included a link in the info section below to my website where you can auto-generate more quotient rule questions for you to practice on. And if you have any queries on what's covered in this video, do post them in the comment section below. So with that, we've come really to the end of part 4 on the quotient rule. Do stay tuned to part 5 where we'll learn how all these rules of calculus that we have covered so far can help us solve coordinate geometry questions involving tangents and normals. Thank you for your kind attention and have a great day of learning.